It's going to be a good day. So there it is. We are going to be doing section 5.5. We're actually going to be finishing up chapter 5. If you've had a chance to look at, I keep saying School Loop. If you looked in Canvas, you'll see that this is actually a very short unit. It's only going to be 4 homeworks long. 3 sections, 4 homeworks. Which means your test, your next celebration is coming up soon. It's going to be, I believe, on February 15th, but I can't remember. Actually, here, wait. I'll have it on the wall. Oh, you guys are writing that stuff down. Yeah, February 15th. But it will be very focused because it's only on a few sections, so that'll be nice. And it's basically more derivative and integration techniques, rules. Maybe not techniques, but... So, the big question for today is other bases. We did base E last unit. We looked at the derivative and integrals with e to the x, natural log x, blah, blah, blah. What happens when your base is not e? And that is what we will investigate today. So, we know the derivative of e to the x is e to the x. The easiest formula in calculus, thank God. But what about a to the x? And we are going to follow our rules with exponentials. So we are talking about a positive base that doesn't equal 1. And you'll see why we need to put that restriction on there. So to answer this, we're going to rewrite a to the x in a rather clever way. So we're going to do, I got a good color. Ooh, but thick. All right, a to the x. Another way we can rewrite this is to say e to the natural log of a to the x. And there's that property that we talked about in the last unit. It showed up on your homework. But remember, when you have a log and an exponent and the bases match, they will cancel out and you're just left with, in this case, a to the x. So yes, a to the x does equal a to the x. So that works. So any questions about that? You got to buy into that. Then we'll take the derivative of both sides. So the derivative of a to the x and the derivative of e to the natural log of a to the x. Now we really can't do anything with the left-hand side because that's what we're trying to find, is what in the world is the derivative of a to the x. So I'm going to leave that alone. I'm just going to write it again. Derivative of a to the x. But now on the right, we did rewrite it so we have base e. So we actually know how to do this now. Anybody remember how we think about chain rule? How would we take the derivative of e to the power of natural log of a to the x? Trey. Exactly. Remember, the derivative of e to the power is e to the power times the derivative of the power. So now we have to figure out how we do the derivative of the natural log of a to the x. Yoshe, can you help us out with that?
So we move the x to the front. So it's x, L, and a. And L and a is just a constant. So L and a x is just derivative is L and a.
Excellent. Let's write down what he said. You got it. So I'm going to go ahead, just have all this stuff here. So we got, again, the left-hand side's not changing because that's what we're trying to find. But to make this easiest, we don't have to do this, but it definitely makes it easier, so it's a good idea. Use your properties of logs to move that exponent out in front. And then it doesn't look like it, but this is just x times a coefficient. The natural log of a is some constant. And we know when you take the derivative of a constant times x, it's just the constant. And so that's what Yojay was saying. So we have e to the natural log of a to the x. And so the derivative of x natural log a is just the natural log a. You guys with me? Any questions on that? We're going to do one more thing to this. Anybody know what that one more thing is that we'll do? Yojay? Exactly. Remember in the very beginning, we rewrote a to the x to be the e to the natural log of a to the x. And there it is. That is our formula for finding the derivative of any base to the power of x. Dun, dun, dun! So, if we compare this and we think about, like, the e to the x, derivative of e to the x is just e to the x. But the derivative of any other base to the x, so derivative of a to the x is a to the x. You just have to remember to throw in the natural log of the base. That's all. So a little extra thing in there. Any questions about how we got that? You don't have to know how we got that. I mean, I do want you to be able to follow these steps. I'm not going to ask you to repeat these steps, but you do have to memorize this formula. At the end of this unit, we will have, finally, all of the derivative and integration formulas that you will have to memorize before the AP. So we'll stop throwing them at you. There'll be other techniques that we'll do, but as far as just formulas to know, this will be the last of the formulas in this unit. So that's good news, right? Finally. All right. Anyway, so there's that. But wait, there's more. But any questions here? Because now, what comes now? Oh, what's right? What about logs? Oh, what are we going to do with logs? So again, we did the derivative of the natural log of x. We know that's 1 over x. But what if it's a base? That's not e. What do we do? I don't know. This one is actually, I don't know. It's a little shorter to derive. But let's look at it. So we're going to do the same kind of thing we did before, where we look at a way to rewrite this. So I shall start off with log, with a pen, log base a of x. Anybody have an idea of another way we could rewrite this? Subra.
You can use change of base.
You betcha. Remember, change of base. And we can change it to any base. Why don't we use natural logs? Because that's already what we know how to deal with. So this is going to become the natural log of x over the natural log of a. And then we're going to take the derivative of both sides. So any questions about the change of base formula? Remember that? Good old friend. So here's another use for the change of base formula. Sometimes we use it to derive other things. So I'm going to do a couple of things in this next step. First of all, I am going to say we're going to take the derivative of both sides. We're not actually going to take it yet. But I'm also going to, again, rewrite that right-hand side to make it more obvious. Because, again, just like above, we were able to rewrite it when we had a coefficient. We have a coefficient in front of the natural log of x. It's not as obvious, but we've got one. We can rewrite natural log of x over natural log of a as 1 over the natural log of a times the natural log of x. And this is now just a coefficient in front of the natural log of x. Because again, a is a constant, so 1 over the natural log of a is a constant. So the derivative of log base a of x, since the derivative of the natural log of x is just 1 over x, it's 1 over x times this coefficient. And that's pretty much it. You'll see this written in different ways. You could just write it like this if you want. A lot of times it's multiplied into the same fraction. So the derivative of log base a of x is 1 over x natural log a. Da-da-da. That's it. So. Oh, yes. Oh, whoops. That got cut off. I need a different color. It's 1. Yeah, right here. Sorry. David was noticing this. A is not equal to what? To what? Ah, that's a 1. Same restrictions as above. All right. So that's pretty much it. You can see a cloud coming up below. I have a little cloud with our formulas. So we actually have a few formulas in here. Does anybody need this, though, before we go to the cloud? Because we haven't talked about integrals. And I'm just going to go ahead and jump right to the integral. We are actually going to look at integrals of exponentials, but not integrals of natural logs. Integrals of natural logs actually require something else. That's called integration by parts. You may have heard other calculus students talk about it. We don't know that yet, so we cannot look at the integral of natural log of x yet. And we may or may not do that this year. It's not an A-B topic, so it's something I usually cover. We'll just see with timing if I need to slow down anywhere. That'll be probably one of the next things to get cut. So it's not that, but if anybody's really curious, I'd be happy to show you. But it's not an A-B topic, so it might get the chopping block. But here are formulas to memorize. Now, we really have kind of 3 formulas, even though it looks like there's 5. Because the top line is really the same formula. So we know the derivative of a to a power is a to the power times the natural log of that base. But if we have something more in the exponent besides just an x, so in this case we have u. We have a function. You got to use chain rule. So you will have to multiply by the derivative of that exponent. And it's just chain rule. And then so the same thing in the next line. The left-hand side just has an x, but if it's not just an x in the argument, you will have to multiply by the derivative of that. And then we'll look at these more. It's going to be easy to get mixed up, so I'll tell you how I think about it. Maybe other people have other ways of thinking about it. I might be wrong. I think we might only have 3 more formulas. Let me look. Maybe 6, I guess. 6. Well, kind of 9. We got the integration and then their partner, or we got the derivative and the partner integration formula, so they're kind of similar. But yeah, I think 9 more formulas and then we've got the list. Anybody got predictions for tomorrow on Groundhog Day? What do you think? Is Phil going to see a shadow or not? Is there going to be 6 more weeks of winter or an early spring? You don't want a spring? You like winter?
Yeah. Spring's when I get allergies.
Oh. Yeah, that does suck. I'm sorry. And that's just never going to go away. What?
Isn't it snowing there? Does that make it one?
I don't know. I mean, it's a scroll. It's up to Phil. It's, it might be snowing tomorrow, but I don't know. We'll find out. If you look at Phil's historical record, even though they call him the prognosticator or prognosticators, he's actually wrong more than he is right. But he's still Phil. We love him. We love him for that. Sorry, Rena and Jenna, that you had to hear that whole story again. All right, so I think most people have written it down. Here's how I think about it. So when you have a different base other than e, you're going to have a natural log of a in there somewhere. So if it's a to the x, you're not, like, if it was just the derivative of e to the x, it would just be e to the x, no division. So there's no division here. You just multiply by natural log of a. But the derivative of natural log of x is already 1 over x. So you're already dividing by x. You're also going to divide by the natural log of a. That's how I remember where to put the natural log of a. Because one of them you multiply and one of them you divide by it. So that's really the only difference. So just remember, if it's another base than e, put a natural log of a in there somewhere. And if you're dividing, divide by the natural log of a. Otherwise, multiply by it. So, and then this guy down here, hopefully you guys can see that this is related. This the integration one is related to this very first one. If you were to take the derivative of the right-hand side, well, the derivative of a to the x is a to the x times the natural log of a. But we don't have a natural log of a over here, so we have this to cancel it out. So this is just directly from that. Isn't that fun? You guys. All right. So here's what we're going to do. I got some problems, and I want you to try them. Now, I actually have all the problems here, but don't worry, I have a handout for you so that you don't have to try to read the little writing. But I'm going to star some that I want you to focus on. And then if you have time before we go over them, you can try other problems. If you don't have a chance to look at them, or we don't have a chance to look at them today, because it is collaboration day, it's going to be shorter. I do have all the solutions worked out in these notes, and I will post them. But I'm going to want you to focus on example 1, example 4, definitely example 10. Let's do 7 and 9. So try those. Oh, actually, I take it back. There's one more. Which one? Let's just do this one. Okay. So take a look at those. You can do them in any order. Let me give you the handout. If you want to get started on them now and you can read them, that's cool. I literally printed out that page, so it's my handwriting. It's not
See, this is all the paper I have left. Maybe I'll just stay there. But I'll have to find some paper. I might actually have enough of the same graph paper to stay with That's all right. You got another leg. It's fine. Yes, sir.
Oh, hang on 1 second. I gotta pause the recording. Whoop. It's so exciting, the countdown, huh? So if you're just joining us on the recording, you can see the solution to number 1. Does anybody use the recordings even though you've been here? I'm just curious. Okay. So would it be worth me, I mean, it doesn't, you can see now that I finally figured out how to do it, it's no big deal for me to do it. Do you want me to continue making recordings? Yeah? Okay. We shall do it! So any questions on number 1, or does anybody, I see some people still writing down the homework. 4, 5, 7, 9, 10. Gotta remember which problems to look at. All right, anybody still need the problems? All right, let's look at 4. So there is 4. And it does look funny, and yes, you can leave your answer like that. Sometimes it really, you'll see unless it really simplifies down super easily and super nicely to slope intercept form, a lot of times it's just left and point slope. And we haven't seen this notation very much, but remember, this is how we signify that we want to evaluate a derivative at a certain value. We use this notation. Sometimes you'll see the 1 written on the other side, like they'll add 1 to get the y by itself, but it won't be combined at all. But any questions about number 4? Anybody need more time looking at number 4? Ready for number 5 then? Number 5 is right there. So, oh my God, there's a variable in the base and the exponent. It's insane! Thank God for logarithmic differentiation, though. This is how you do it. So remember, take the natural log of both sides. Then you can use the power rule for logs. Put that exponent out in front, multiply by it. And then when you take the derivative, it's product rule. And yes, you could leave your answer basically in this form. I mean, I'd still have to multiply by y on the other side. You don't have to get a common denominator. And I hear people using the word simplify all the time. Like factored form, people call, some of you guys are calling simplified form. Or putting it in a single fraction, some of you guys are calling it simplified form. It's not simplified, it's just another way to write it. It's just often when you're going to use these derivatives or whatever it happens to be, you're going to like go further and do something with it. It's usually more useful in a factored form or in a single fraction. So any questions about that one? Yes. Because the base is not a constant. You can only use that rule when the base is a constant. All right. Anybody one more time looking at this one before we go to 7? Okay. Bum, bum. Okay, while we got people writing it down, here's my dream schedule, like school schedule. I don't know if I mentioned it to some classes. I apologize if I've already mentioned it to you guys. So we got this whole law coming down the pike that says high schools can't start before 8:30. Fine. I don't think it's going to do anything to help sleep deprivation of you guys. But here's what I think could help with everybody. What we did last year, where Wednesday was a work day. Monday, Tuesday, A day, B day. Wednesday is a work day. Wednesday, teachers can have meetings. Teachers can meet with students. We could come in person and meet if we wanted to have a study session. We could just meet online. We could not meet at all and we could just work, whatever. But Wednesday's a work day. Thursday, Friday, A day, B day. Wouldn't that be great? We can't do that right now because the state says we have to have so many instructional minutes. And if we did that, our like Monday, Tuesday, Thursday, Friday would go to some ridiculous, I can't remember what it is, but we'd meet like 2 or 3 hours later than we currently do now. It'd be awful. So we can't do it now. But We need to write to our state legislators and say, hey, it's not that we need to move the school day. We need to have less time. I mean, we got to change with the times, man. We can do things more efficiently. Less time in the seat. Ugh. Anyway, that's my idea. Last year we could get by with that Wednesday because of COVID. The state gave waivers for the instructional minute requirement. Anyway, here's number 7. That's it. That's it. Nothing else. Yeah, don't forget your plus C. Did you guys like my memes on the test? Hopefully that was a little reminder. All right, you ready for number 9? I was trying to remember the next one I had you guys do. Number 9. So I had some questions about number 9, like how to get started. So in general, just like we had before, if you're taking the integral of e to a power and you're not sure what else to do, use substitution, letting u equal that power. Same thing applies when your base is not e. If you have a base to a power and you don't know what else to do, let u equal that power and see where you go. Yes. Okay. But the other thing to remember, this is a definite integral, so you have to change your limits of integration as well. Yes, Marcus.
To get this on a test or something, would it be fine to write it as
15 over 4. Wait, say that again?
15 over 4 times that.
Oh, yeah, it's equivalent, so yeah. Yes.
I think we can also do is change 4 to the x over 2 to 2 to the x instead. Because it's 1/2, so you do the 1/2 thing first, and then you do the x second. So you take 4 to a 1/2, which is 2, and then so 2 to the x. So
Oh, yes, you could do that. I didn't even see that. That's true.
Yes.
That is true. For those of you online, or those of you here that didn't catch what he was talking about, you could... Let me rate that better. Can't really see the x. This is equivalent to this. And then you can take 4 to the 1/2 is just 2. So yeah, very nice that you saw that. Any other questions or comments about number 9? Oh, you're ready for number 10? The number 10 is this one. It's been a while since we did area, huh? So it helps to draw a picture to see what's happening. Now, I actually don't know if this is what the graph looks like, but it doesn't matter. The main thing that you have to know with your graphs is where the x-intercepts, y-intercepts, and is it above or below the x-axis? And because of this expression here, 3 to the power of something, 3 to any power is always positive. Now, once we multiply here, because sign could be positive or negative, but between 0 and pi, sign is also always positive. So all I know is that this thing, this entire equation, is always positive between 0 and pi. And because the sign of 0 and the sign of pi, they're both 0, I knew I had x-intercepts here and here, and then in between it's always positive. That's why I drew the graph the way I did. I honestly have no idea if this is what it looks like. But that was enough for me to set up the integral. So now I know that the area is always above the x-axis, and my limits of integration are going to be between 0 and pi, because that's the area I'm looking at. So any questions just setting up the integral? Our next unit, we're going to be doing a lot of stuff, a lot more stuff with area. And this next unit is, you may have, again, if you've been talking to other calculus students, you're just doing stuff on your own. That's when we're going to start rotating these areas and creating volumes of revolution and stuff. So we definitely want to think about how to draw these pictures with or without a calculator. But then once I did that, then it's u substitution. Again, letting u equal just that exponent. And then we went. The other thing that I wanted to point out, you didn't have to do this step, but I just want to remind you. Once I did the initial u substitution, so this line right here. Notice my limits are going from 1 to -1. The bigger limit is on the bottom. And I've had a lot of questions about that. I had to put it that way in the beginning. Because when x was 0, u is 1. That's what I have right here. So where the 0 was, I had to put a +1. But when x is pi, u is -1. So where the pi was, I had to put the -1. So it seems like it's going backwards, but I really had to do that. And then I also had this negative here that made this negative here. And then I decided you don't have to do this step, but to keep track of the negatives better, remember when you switch your limits of integration, it just negates the integral. So I went ahead and did that. I switched the limits and then negated that to make it positive. And then it was less negatives to keep track of throughout the rest of the problem. But you don't have to do this step to get here. I just wanted to point that out what I did. So any questions about that? Yeah, Subrath.
Can I read my answer as 3 over ln 3 minus 1 over ln 27?
I gotta write that out. Say that again.
3 over ln 3 minus 1 over ln 27.
Yeah, if it's free response question, yeah. Any other questions? Alrighty then. Did anybody want to go over any of the others? If you tried them? Yeah, Luca?
Number 6.
Number 6. Shoop, there it is. So I don't know if you just wanted to see it or did you have a specific... Do you want me to walk through it question?
Sure.
Walk through. Okay. So again, anytime you see the base and the exponent both being a variable, use logarithmic differentiation. So that's what I did here. So take the natural log of both sides, so then you can rewrite it. And actually, I don't want all of that out. But then I did, you could have written this as a product and done product rule. I wrote it as a quotient and did quotient rule. But again, 1 over the argument times derivative of the argument on the left-hand side. And then bottom times derivative of the top minus top times derivative of the bottom over bottom squared. And this one simplified really nicely because x times 1 over x is just 1. And then multiply both sides by y. Now, it turned out this one wasn't that bad, but notice I never put it back in terms of x because of what I was going to do with it next. I'm going to find the value of the slope at a point, and I have the x and the y coordinate. So I didn't have to put it back in terms of x. I went ahead and let all the x's equal a 1 and the y equal a 1 because that's what the point said. And then you just wind up with that. Any other questions on that or anything else? All right. Then that's a wrap. We're done.